And in the back room, Grant Justice is taking their wonderful webcast feed and streaming it out to YouTube, so give Grant a hand. All right, let's get started. Good evening, ladies and gentlemen, and welcome to the Space Telescope Public Lecture Series. I'm Dr. Frank Summers of the Office of Public Outreach. And when you came in today, there may have been these lithographs on the tables here and over there. Tonight's lithograph is Galaxy Cluster Abell 2744, which is a cluster so large that it produces gravitational lensing. And you want to know what gravitational lensing is? Well, turn over on the back, and we have a few paragraphs to tell you about the amazing things that are happening inside this galaxy cluster. If you did not get one on your way in, pick one up on your way out. Our talk tonight, gravitational wave astronomy, talking about some of the discoveries that won the Nobel Prize last year. Next month, we will have star formation in Orion from Will Fisher. That will be on June 5th. And Orion is really one of the coolest places where we can study star formation because it's the nearest star-forming region where we've got the full range of stars being born, from the smallest to the very largest. And so it's one of our prototypical star-forming regions. So great place to learn about star formation. On July 3rd, David Nataf from Johns Hopkins will be talking about the Milky Way's bulge from a hypothesized blob to a remarkably detailed picture. All right. The structure of the Milky Way has, evolved over the years, and he'll give us a great history about its core of the galaxy, the bulge. In August, we have our infamous Mr. or Ms. TBA, which means I've got a little work to do this month. It's sometimes hard to wrangle speakers for the summer months, but I always do end up getting you one. When I do have a speaker, you'll find it on our website. If you go to your favorite search engine and type in Hubble Public Talks or Space Telescope Public Talks, you should find this page, which has the list of the upcoming lectures over on the right-hand side. On the left-hand side, we have the links to our webcasting, both the live and on YouTube. We also have our past lecture, our archives, which go back to 2014 on YouTube and all the way back to 2005 with our STSCI webcasting. Lots and lots of lectures for you to watch. And you can also subscribe to our email list and get 1 or 2 emails a month reminding you of what's coming up and when our webcast is posted. The announcements, as I said, sign up on the website, or if you can't do that, you can write your email address on a piece of paper and hand it to me at the end of the lecture, and I'll make sure you are signed up. If you have comments or questions, we have an email set up, publiclecture@stsci.edu, where you can ask questions. Social media, we have Facebook, we have Twitter, we have YouTube, we have Instagram. If you're into that, Hubble and James Webb and Space Telescope provide feeds, social media feeds for all of you. I myself do a little bit with Facebook, Google+, and Twitter. So if you'd like to find out more about me, you can follow me on social media. The weather is nice tonight. We would be able to go to the telescope across the street, except Johns Hopkins University scheduled an event there tonight and usurped us. So I know, last few months it's been bad weather and we haven't been able to do it. This month it's good weather, but I'm sorry, there was another event already scheduled. So we will not be going to the observatory this evening after the talk. However, as always, you can go to md.spacegrant.org. You'll find this webpage about their open houses on Fridays. In this box over here on the right where it says observatory status, that is where you will find out whether or not they're open this Friday night or next Friday night or every Friday night. And you can check this if you would like to look through their telescope. And now, the news from the universe for May 2018. Our first story tonight, Gaia DR2, which stands for Data Release 2, redefining the Milky Way. And I had such a geek out last week when this data was released. I had to show you some of this stuff. So let's start. Let's start with stellar databases, okay? So this is a photograph of the night sky showing what constellation? Orion, thank you very much. And you can see the stars here of Orion. And the data for these 7 main stars in Orion might look something like this. And so here we have the names of the stars on the left, the RA and DEC, the right ascension and declination, their position on the sky. You have the magnitudes, which is their brightness. We have the spectral type, which helps give you their color, etc. And from these stellar databases, we could create a picture of Orion. And so a visualization of Orion on the right, coming from just the data, can produce an image like that, comparable to the picture. All right? And so that image on the right is only from the data. All right? And so the data that goes into that picture comes from the Hipparcos catalog, which has 118,000 stars. And it's got the positions on the sky, and it's got the spectral types and the magnitudes and the parallax, the 3D distances, allowing us to visualize the universe. But Hipparcos flew as a space mission that flew between 1989 and 1993. And the data set came out in 1997, 21 years ago. What have we been doing in the meantime? Well, the Hipparcos catalog covers just a small part of our galaxy. 100,000 stars sounds like a lot, but when you compare it to our galaxy, this is a visualization of our galaxy, an artist's depiction of our galaxy. And this white spot here, that is the extent of the Hipparcos catalog. Okay? It's actually 20 times the Hipparcos catalog because it's really the Tycho catalog from which the Hipparcos is a subset. Okay, so it's like if our galaxy is a pizza, it's the size of a sausage, little sausage piece on our pizza. Okay, and that was the state of the art for the last 20 years until last Thursday. All right, they've been doing the Gaia mission. And the Gaia mission is designed to take Hipparcos and really do it well, okay, and go full bore with it, okay? On Thursday of last week, Gaia released 1.7 billion stars. Not 100,000 of Hipparcos, not the 2 million of Tycho, 1.7 billion. And this is not an image. This is a data plot from Gaia. This is plotting the color and brightness of all 1.7 billion stars across the entire night sky. It is so remarkably detailed, it looks like a photograph, but it's not. It's a visualization of a data table. Think of an Excel data table with 1.7 billion entries, and you're plotting each one of those points and combining them all together. That's the picture you get. Yeah! This is why I was geeking out last week. It's amazing. And let me show you some of the details, because if we zoom into the center, all right, you can now start to see the pixelization of the thing. And what we are plotting here is all of those stars. And it looks like we've got gas clouds, dark dust clouds in there, right? There's no dust clouds in this database. What you're seeing here is the absence of stars. Now, it's of course due to dust clouds that are actually out there, but we're not plotting the dust clouds, we're plotting only the stars, and you're seeing the absence of the stars in those regions where there are dust clouds. This database is so remarkably detailed that it gets pictures of the Large Magellanic and Small Magellanic clouds that are almost 200,000 light years away. These are satellite galaxies of the Milky Way, and you get these remarkably detailed images of them, what look like images, when you plot up the data. Oh, and by the way, this white spot down here that looks like it's in the Small Magellanic Cloud, it's not. It's in our galaxy. This is the globular star cluster 47 Tucanae. So you've got 1.7 billion stars in this database, and from it, just the star brightness and color, you get a remarkably detailed image. But it's got a lot more, because they measured these stars over and over again to get their motion on the sky, their motion relative to the sun. And so measuring all those velocities relative to the sun we can measure the motion of our galaxy. So this is the plane of our galaxy here. Our galaxy is shaped like a pancake, and that pancake is rotating. And so when we look at their velocities and we measure the Doppler shift, we get an image like this. So here, the blue is coming towards us, and the red is going away from us. All right? So this is the radial velocity map. These are motions on the sky relative to the sun. And so inside this circle here, in the central region, those are the stars that are closer to the center of the galaxy. And they're rotating faster than the sun. So the ones on the right-hand side, that blue blob there, that's approaching the sun. And the red stuff on the left-hand side, that's going away from the sun. Alternatively, the outside part, beyond this, outside this circle, are stars that are outside the galaxy, and the sun is moving faster than them, so the sun is moving away from this red blob over here on the right and towards this blue blob over here on the left. We're seeing the rotation of our galaxy in detail as we've never seen it before. Okay, I mean, if I showed you the plots of what we used to know about this, they're really patchy and just, they sort of get the idea, but this caused an astronomer friend of mine, when I showed it to her this afternoon, she just went, oh, and she just started going, her mind just started racing about all the various things they could do. If you looked up the Twitter hashtag GaiaDR2 last Thursday and Friday, you saw a ton of astronomers just geeking out and trying to, get initial looks at this data set and trying to find all sorts of cool things. There's going to be so much discovered from this. The discoveries have just begun. And in particular, take a look on this red blob over here on the left in the center. What are these blue blobs here? What are the things on the left side that should be going away from us look like they're approaching us? What are the details there? Some of just the obvious things to look at. And of course, there's a tremendous number of much more detailed questions. So Gaia is going to provide an amazing number of discoveries. And it expands the 3D distances that we know of in our galaxy. We go from that sausage on the pizza to a pepperoni, a really large pepperoni on our pizza, okay? That here on the right-hand side, that spot on the right-hand side of Gaia DR2, that is 1.7 billion stars, the extent of 1.7 billion stars. And when you look at that, you can start to believe that, oh my gosh, yeah, I guess the galaxy really does contain 100 billion stars, if that's all that's covered by 2 billion. All right, and so more will be coming, and hopefully in about a year from now, I'll be able to have a speaker in to give a talk on all the amazing discoveries from Gaia and its data release 2. Our second story tonight, 28 years of Hubble. Hubble launched on April 24th, 1990, and every April, we in the Office of Public Outreach have this huge pressure pushing down on us. Come up with a really cool image to celebrate Hubble's anniversary this year. So the image processors put their thinking caps on, and this year they decided to go with the Lagoon Nebula. Okay, now this is not a Hubble image, this is a ground-based image, right? And actually, the Lagoon Nebula is so large that Hubble can't really cover this without many, many, many pointings. So the Hubble image that I'm going to show you is just this region in the heart of the Lagoon Nebula. Because you've got all this beautiful red gas out here that's sort of been blown out and that's ionized, but where the star formation is still taking place is right here in the heart of the Lagoon Nebula. And when you look at that with Hubble resolution, using specific filters to pull out the elements, you get that. All right, this side of the room say ooh, and this side of the room say ah. Ready? And hold on. Thank you. Let me zoom in and show you some of the cool details. All right, so right in this central region here, we zoom in. You can see that there's a massive star there. It's sort of hidden behind this curtain of dark gas. Okay, this is an O star. This is a really massive star, and they tell me it's only 1 million years old. It's just been born. Yeah, 1 million years is not old for a star, okay? And you can see how it's illuminating all that gas in behind that dark that dark cloud. And it's also producing things like there's this bow shock down here over on the left where the wind from that star is pushing back the gas around it. You've got these pillars, etc. I mean, there's an incredible energy, not only in the radiation, but also in the wind coming from that star. We've got a lot of other cool things, like on the left here, we've got some ionization fronts. There's some stars that are just off the image of the Hubble, and their energy is coming down and creating these ionization fronts here on the left, and also this gorgeous ionization front over here on the lower right, where you can see that the energy, the ultraviolet radiation is heating that gas, causing it to ionize, go from neutral gas to ionized gas. And then we got these tiny little pillars in the upper right there, where the gas is being eaten away, and all you're left with these small little blobs that have been ionized, that have little ionization fronts on top of the pillars as everything else gets stripped away. So this is the visible light image, but Hubble, of course, has really good infrared sensitivity since servicing mission 4. And visible light, we also took an infrared that looks like that. Ooh, quite different, eh? Let's go back. Visible light, infrared. Visible, infrared. Look at all the stars, all right? The longer wavelengths of infrared passes through that gas, and you can see all the stars behind it. The Lagoon Nebula is toward the galactic center, so it's a very dense star field that you're not seeing in visible light because, of course, the gas is blocking it. And when you see the dense gas here in this visible light, all right, in here, let me go back and you can see how dense the gas appears in the invisible light, right? All of this central gas looks like it's really dense, but infrared shows you that most of it's not that dense, and that the infrared light can pass through it, but some pockets are really dense because when they're dark in infrared, they're really dense pockets of gas. And so by using both visible and infrared, we gain different pictures of this, of these regions. So we put together a visualization of it, and when we were discussing it, we said, oh, we got all these structures that are coming from the ionization and from the winds. And we said, oh, you know what this is like? It's like a sculpture garden of gas and dust. And that's what we called our visualization. And that was a 2D zoom, and now we give you a bit of a 3D feel as we do some pans across these different sculptures in the nebula. And that's how we wished Hubble a happy 28th anniversary. All right, our featured speaker tonight is Dr. Andy Fruchter, whom I met at Berkeley while he was doing a Hubble fellowship at Berkeley, and I was doing my PhD work there. Andy's always been known as a very jovial and very friendly guy, and I'm so glad that we have him here tonight. He did his undergraduate work at Harvard, then spent some time at Cambridge in England for a bit before doing his PhD at Princeton. He then came to Berkeley and did his Hubble Fellowship there. And let's see, he went to the Carnegie Institute in Washington before coming here to the Space Telescope Science Institute, where he's been how many years?
I don't know.
It's just around 20 years, because you're a little bit longer than me.
Yeah, exactly.
I've only been here 17 years. Not very long by Space Telescope standards. His functional job, but his astronomy work has been in pulsars and in supernovae and
Gamma ray bursts.
Gamma ray bursts, yes, very gamma ray
yeah.
bursts. And he'll talk to you tonight about gravitational wave astronomy. I should also mention that his functional job here is in the Science Mission Office, helping to run the science program within this building. Ladies and gentlemen, Dr. Andy Fruchter.
Here we go. Okay. Excuse me, I'm getting over a cold, as many people are these days. So, all right. Let's see. Is that... There we go. Okay. All right. So, welcome. Tonight, I'll be speaking about the very beginning of gravitational wave astronomy. In the last 2 years, we have opened up the universe in an entirely new way. We have detected gravitational waves from black holes, binaries, and the black holes in these binaries are from our stellar mass. We know that there are huge black holes in the center of galaxies, but these black holes are bigger than any black holes that we knew existed that existed from stars. Many of them are. We've seen black holes merge into two black holes come together and merge into a single black hole, right? And you'll see that today. And we've located a neutron star binary, which emitted gravitational waves, giving its position and its distance. And we saw the light that we're seeing, we saw light from it, gamma rays, radio, optical, infrared, and we saw the radioactive decay of material flung out from these neutron stars. And we believe that this material is the basis of most of the heavy elements in the galaxy, in the universe. That is, supernovae produce oxygen, carbon, hydrogen, things like that. Also, winds off stars do that too. But to get things like gold, lead, uranium was very hard from supernovae. People didn't know how to do it. We think that they come from merging neutron stars now. So that wedding ring on your finger, if you have one, that came from a neutron star, we think. Okay, so in this talk, I'm going to start off with a bit of background on what gravitational waves are and how we detect them, right? And because that's how we did all of this science. It was the basis of all of this science. And then I'm going to talk about, again, some of that astrophysics that I just gave you a broad overview of. And then I'll talk a bit about what we might expect in the future. So Einstein had so many great insights that it's hard to keep track. But the one that's going to be most relevant tonight, though there's another one that will be later, is the basis of what we call general relativity, his theory of general relativity. And one of the insights in the formation of that theory was to realize that he could explain many of the ideas that he had by conceptualizing gravity as a change in the geometry of the universe. So that if you imagine that this is the sun and this is the Earth. Now, why does the Earth go in a circle around the sun? Well, the Earth in Einstein's idea wants to go in a straight path. Right? It's in free fall around the sun, so it should just go in a straight path. It doesn't feel that it's accelerated. It thinks it's going straight. But what Einstein realized is, well, if it curves space-time, right, then a straight path is just like a great circle. If I walk straight out of this room and keep going and then swim a bit and then walk a bit and then swim a bit, I'll end up right back where I started, right? All the while I'm thinking I'm going in a straight line, but in fact I'm doing a curve all around the Earth, right? And in the same way, in this conceptualization, the Earth is going on a curve, is going straight around the great circle around the sun. Okay? And so that so basically gravity is bending space-time, it's bending the shape of space in the way that gravity feels, that our bodies feel it, right? Now, he also realized that just like in electromagnetism, or very similar to electromagnetism, if you accelerate an electron or charged particle, you'll radiate. He realized that the motion, that accelerating mass can also produce gravitational radiation. Okay, so here's a picture of that. So you can imagine here are two objects, well, you'll find out they're black holes, modeled black holes, right? And they're in a binary. Now, what they're doing is radiating. These are gravitational waves going out, and the gravitational waves actually are changing the shape of space-time because of their energy, and the energy deforms just like mass, gravity. And then they've merged, and the gravity waves stop coming out. We can see that again if we want. Note also that when you emit gravity waves, you're emitting energy. So the binary is losing energy, so the two stars fall in towards each other as they lose that energy. And they put out more energy, they fall further in towards each other. They put out more energy, they fall further. And eventually they merge, right? So gravity waves can actually causes binaries to merge. Now, if they're very far apart and moving slowly, it could take much longer than the age of the universe. But many objects are massive enough and in fast enough orbits that they'll radiate away their energy, and in that we can hope to see it. So what would a black hole merger look like? Right? So this is if we were actually looking at it with a telescope. Right? Two massive black holes. Now let's see, was it going to show me there? No, it's not showing. Let's see, it's not. There it is. But if I click it, okay, it worked like that. Okay. So let it go. Nope, go to the next one. It works differently on this than it does on a desktop. Let's start up again. So you're seeing here the two black holes go around. This is the gravitational lensing that Frank spoke about earlier. These are the black holes changing the light, changing the shape of the objects behind them because they're creating a distorted lens. And then here they are basically coming together into one final black hole. It sends out some gravitational waves here. It changes shape as it does its final dance. And that is what you would see if you could actually take a Hubble image of a merging black hole. The problem is, this image is about 1/1,000,000th the size of a Hubble pixel. So it's going to be hard for us to get that image, right? That is sort of a visualization that they did out of Caltech. But so you're really going to, if you want to see this, we're going to have to see it some other way. Now, there is a project going on right now to image the black hole at the center of our galaxy. And it's a huge project using radio telescopes all across, millimeter wave telescopes all across the Earth. And they're going to try to get a picture, basically making the Earth, this antenna the size of the Earth, trying to get that picture. And they're still working at it. It's a very hard project, but we may get it. And they may be able to resolve the black hole at the center of the galaxy. But to do that, that's our closest large black hole, right? To do that in another galaxy is way beyond our means right now. So I'm going to suggest we do something crazy. Let's try neutron stars instead. Now, they're not much bigger. In fact, this is this was put together by colleagues at Northwestern University who had a conference, and this is a neutron star over Chicago. That's the size. A neutron star is about, I don't know, 10 miles across or so. And so they're not very big, but they're made of matter. Black holes are dark, right? Neutron stars are matter still. The way you form so when the sun runs out of fuel, it's going to collapse down to what's called the white dwarf, which is a star that is basically just atoms packed together as tight as you can get them. And what supports them is the fact that electrons are called fermions. They're a type of particle called fermions. And fermions to be packed together. They're very antisocial. There is another type of particle called bosons. It depends what spins they are. Bosons love to be together. Fermions hate it. And you just basically, you can push and push and push and they won't go any further. But eventually, if you push hard enough, you put enough matter onto that white dwarf, it says, okay, well, I just can't take this anymore. I'm going into the nucleus. And the electron goes into the nucleus and it combines with a proton, and the charge of the proton and the electron cancel, and they produce a neutron. And so the star, all those electrons get captured by all the protons, and what is left is a star that's just full of neutrons, basically. Just neutron matter. And that's what we call a neutron star. And neutrons are also fermions, so again, it takes a lot of matter to make them do anything else, but eventually if you put even more matter onto a neutron star, it will collapse down to a black hole. And so if you merge two neutron stars, you will often have enough matter, we think, that they will leave behind a black hole. We'll be seeing that later. So neutron stars are also the basis of what we call pulsars. Pulsars are these magnetized neutron stars which are spinning. And they basically produce, basically here, this becomes like a lighthouse. And that swings around, and if it happens to point at your direction, a light flash, you see it flash go off, and then it swings away and it goes off. And then it points at you and it's bright. And then it goes away for most of the time and it's dark. And so you can use that as a clock. You can say, okay, I can watch, and it's very regular because it's a massive object spinning. So you can say, okay, know that neutron star spins, say, 30 times a second, right? So then I can just count those times it's spinning. I can count the clicks as it goes by. Now, if it's coming toward, if it's a binary, sometimes it'll be coming towards me, and sometimes it'll be coming away from me. And it'll have a Doppler shift. So it's coming away from me, going, ooh, right, if you turn it to sound. We're going to be turning some other things into sound later, and it'll sound much better than me. And so you can use that as a clock. So you can say, okay, I know when I can follow that neutron star in its orbit. Okay? So what happened in the 1970s was this pulsar, 1913 plus 16 was discovered. And this pulsar is in an orbit with another neutron star. The other neutron star is not a pulsar as far as we know. If it is, it's not pointing towards us. But we can measure its orbit. And its orbit is changing. It's actually getting faster. And that's what this curve is showing you here. The orbit shrinks by about 7 meters a year. So that's the amazing thing about this pulsar. It's a very regular clock, so you can do incredibly precise measurements. And it radiates about 2% of the solar luminosity, about 2% of the energy of the sun is what it's radiating. So it's losing energy, and that's causing this orbit to decay, right? Now, our solar system doesn't radiate much energy. The solar system radiates about 5,000 watts in gravitational energy, so less than a hefty air conditioner on a summer's day, right? So that's not, you're not going to get much energy out of the solar system that way. But you'll see that some things give out a lot of gravitational wave energy. And this will merge in about 300 million years. Now this was discovered by Hulse and Taylor, Russ Hulse and Joe Taylor. Joe Taylor was my advisor at Princeton. He actually Well, first, they got the Nobel Prize for this in 1993. Russ Hulse was his grad student at the University of Massachusetts, and Joe was then at the University of Massachusetts and then moved to Princeton. And Princeton figured this was coming, I think. He had some trouble with the pulsar company, though. While I was there, they sent him a cease and desist letter. They said, the pulsar name is trademarked. And so you cannot use it. Well, we know how that turned out. But so we still use it. But the pulsar company, I think their watches are still around. So, all right. And they got this prize for it was for discovering this pulsar mainly, and which could give insight into gravitation, which it did. That was indirect. So what you were seeing there, right? What you're seeing there is the loss of energy due to gravitational waves. This was proof, and that line there is Einstein's prediction, and the dots are the data. Right? So it's incredibly good agreement between what Einstein predicted and what we observe. And there are so much information from this that you can solve for all the parameters. There's no assumptions in this. And you solve for the entire system and you get that agreement. It's astonishing. So this was a remarkable confirmation of general relativity. But it wasn't the direct detection. It was an indirect detection of gravitational waves. So there was still another Nobel Prize out there to be gotten. So what does it mean to detect a gravitational wave? What is a gravitational wave? So I've told you it's energy, but what does it do when it goes by? It does this. It distorts space and time. And it does it in a funny way. So that if a gravitational wave was coming this way, right? I would be stretched this way and be made thinner this way. And then I would be pushed down like this way and be made broader this way, simultaneously, right? So it's a simultaneous stretch and pull that goes on. And in fact, this is just one. There's another mode that's at 45 degrees like this, but I am not going to try to do that mode. I'll kill myself. Okay. So, and then here in the blue, I've got a version that shows it as a slinky. Right? So that's what a gravitational wave does. It stretches and compresses space-time. But gravity is weak. What do I mean by gravity is weak? Well, every time you look at a refrigerated magnet, you're seeing that gravity is weak. Right? You have the whole Earth trying to pull down that little tiny magnet. And what this little tiny magnet's on next to a refrigerator, right? And it's resisting the pull of the whole of the Earth. And that's what we mean by gravity is weak compared to electromagnetism, right? It takes a lot of matter to have the sort of force that electromagnetism does with just a few particles. And so if we ask, what is the brightest source we would expect to see about once per year? Right? The longer you wait, the brighter some source is going to be because something will happen closer, right? But if you say, well, we had to do predictions of how bright will things typically be? And we had estimates that were between, a factor of 100, really. And we could guess about how what you would need. And we figured, people thought it would be about 1 part in 10 to the 21. That's 1,000 billion billions. It's a tiny little bit, but what does that mean? What do it mean? How much? It means that, first of all, you're not going to feel it. But if you were say I built a detector that just, say, is 4 kilometers long. That's what these are. The Laser Interferometer Gravitational Wave Observatory, LIGO. There are 2 of them because you want at least 2 because, well, it helps you localize them, but also you want to be sure that if you see something, it's real, right? So that was one of the reasons they built 2. And they're well separated. So if a truck goes by Livingston, Louisiana, you don't feel it in Hanford, Washington, right? And they're 4 kilometers long here, all right? Now, and the waves will come by, and a wave will stretch this arm while it shrinks this arm. And then it'll stretch this arm while it shrinks that arm, okay? And that's why you build it in this sort of right angle configuration. But if you've got something 4 kilometers long, or about 2.5 miles long, what does that size, 10 to the minus 21, mean in practice? Well, this is a hydrogen atom. That, we're now going in to see the scale of what you have to measure. That's a proton. You have to measure a tiny fraction of the size of the proton. That's what one of these waves going by will cause this arm to shrink by and expand by. So it's incredibly precise. It's so precise that you think these people are crazy. Right? There's no way, and many people thought that for a long time, right? These people are crazy. We'll give them the money, yeah, well, you know, they'll shut up. But they're crazy. And to believe that you could do this, right? Well, they've done it. It's amazing. And so I'm going to give you a video here, a short little video, where it introduces Ray Weiss, who is the person who had the idea, basically the person who had the idea of using an interferometer, which is, it'll explain here, that the use of light to measure the distances and to get this very, very precise measurement. Oh, do we have, well, oh, wait, I don't know if we checked the sound. Hopefully we have sound. Do we have sound? We'll check, we'll find out. No, we only have sound from here. Am I gonna have to do this?
The laser beam is split and
hear that?
down a pair of long perpendicular tubes.
Let me go back to the beginning. But I need sound.
Can come. I'll come change your settings.
Yeah. We definitely need sound because there's some really cool sounds later. But let's see, where's the speaker on this thing? Oh, it's right here. All the way up to, yeah, that's right. Okay, let's do that.
To measure the stretching and squeezing, Ray turned to a device called an interferometer. A laser beam is split and sent down a pair of long perpendicular tubes, each precisely the same length. The two beams bounce off mirrors and recombine back at the base. The light waves come back lined up in such a way that they cancel each other out.
And you add them together, you get nothing. You get a zero, a big fat zero. No light gets detected at the photodetector.
But when a gravity wave comes along, it distorts space and changes the distance between the mirrors. One arm becomes a little longer, the other a little shorter. An instant later, they switch. This back and forth stretching and squeezing happens over and over until the wave has passed. As the distances change, so does the alignment between the peaks and valleys of the two returning light waves, and the light waves no longer cancel each other out when added together in the recombined beam. Now some light does reach the detector, with an intensity that varies as the distance between the mirrors varies. Measure that intensity, and you're measuring gravity waves.
The light takes longer time in here than it did in this arm. Now it takes a shorter time, and these things don't cancel so beautifully anymore.
Okay. And as remarkable as that, so you're measuring a tiny fraction of the wavelength of light, but you have to align these things incredibly precisely. And there's another trick that they do, which isn't talked about a lot, but they actually put another mirror in here. And so the light goes back and forth about 100 times. It does about 100 round trips in there. So rather than being 4 kilometers, these are basically more like 400 kilometers as a result. So you get that extra factor of 100. So that helps a tremendous amount, right? And they have a number of tricks in here that are simply amazing, that basically turns this 20-watt laser into 100 kilowatts here. So it took many years of research and development and from many brilliant people, but it has produced a remarkable device, right, that can measure these incredibly small changes in distance. Now we can use general relativity to predict what we should see if two things merge, if you had a binary merge and the wave came past by us. What would it look like in this detector, right? And what you see, you'll see, and you'll get something like these wiggles here, and that's it, the wave passing. And what happens here is that it's going it's relatively slowly. They get closer together, it speeds up, goes very, very fast, then they combine, and then they're going to spin down. You get a little shaking of the object, right, as it settles down here. This is very hard to measure because it's weak, but we have a little bit of indication. And here you can see that these are two black holes that were actually seen. You can see that they're, in the end, just before they merge, they're moving at almost the speed of light. Incredibly violent process going on here, right? Two black holes in a binary coming together. Now, what they do is they look at, I'll show you in a minute what the waveform looks, what they actually look at. What they do is they take GR and they take all these different predictions, like what could all the binary orbits look like? And then they try and fit them to the data, right? And when you do that, when you finally get a good fit, you get, if you have a, say, very good signal to noise, you learn everything about these objects. It's amazing. You get their mass, you get the masses of the two objects, you get how circular or how elliptical the orbit is, you get if they're spinning or not, you get how that orbit is oriented with respect to Earth, right? Is it tilted this way? Is it, you're looking at edge on? And you get the distance, you even get the distance, because if you've got all of these other things, you can predict how bright it should be. And then you look at how bright it was at Earth, and you say, well, the only way it could be that, I know how bright, it's like if I held up a flashlight, and you know how bright that flashlight is, you could guesstimate how far away I am by how bright the flashlight looked to you. You can do the same thing with this binary. So you can get everything about the binary in principle if you have really good signal to noise. So it's an incredible system, incredible theory and incredible system. Of course, so we don't have infinite signal to noise, so you could do well, but you can't do perfectly, but I'll show you that later. Okay. This is what the first detection looked like. So what you see here, the best fit is that predicted line, right, is what they call predicted, and the heavier line is the data. And they're two different, right, this is Hanford in Washington, this is the Livingston in Louisiana, and here they've been aligned because, of course, depending on the direction of the light wave, the gravity wave, it takes about 1/10 of a second for it to get from Louisiana to Washington. There's another way to look at it and to say, okay, you maybe have heard of sonograms, right? What you can plot here is the frequency of these wiggles versus time. And you can see that it goes up with time. It starts low and goes high. I'm going to play this one for you. Now, it's very brief, so you'll have to, I guess we also have to do this. Not too impressive. We've got a more impressive one coming later. But this one just goes like, yeah. That's the problem with these black holes. Just quick like that. No fun at all. Let's see if we can get it to come back. Let's try again. Unfortunately, I couldn't get the here we go. Okay. That's the sound of two black holes merging. Sounds like they're a pair of chipmunks, but it's actually two black holes merging. Okay. Yeah, it's more, conceptually, it's more impressive somehow. All right. So they detected, was the merger, we know it's two black holes from the masses and their sizes. The black holes individually weighed 36 and 20 times, so they were both about 30 times more massive than the sun. This is huge. The biggest ones we've seen, in binaries, when we look at other stars and ask their orbits around black holes, it's been about 15, 20 solar masses maybe. 10 is usually very high. And so these are incredibly high. In fact, some people have suggested that maybe these are primordial. Maybe they didn't even come from stellar evolution. We don't know. We think that they can probably come from stellar evolution, but it's up in the air. Because we're finding a lot of these, and it isn't completely settled why we're finding so many. they came together and formed a new black hole of 62 solar masses. Now 36 plus 29 is greater than 62, right? 3 solar masses of energy were radiated as gravitational waves. That is more energy that came out of all the stars in the visible universe in the same amount of time. Came out in gravitational waves. Now you didn't have to duck because gravity is weak. But even so, right, the merger happened, it was far away, so it happened 1.2 billion light years away, and so 1.2 billion years before we detected it, so it's a ways. But if gravitational waves were light, it would have looked, you would have seen a star as bright as the full moon. Right? If your eyes could focus gravitational waves and detect them the way you detect light, then on that night, if you had looked up, you would have seen a star for a brief amount of time that was as bright as the full moon. In fact, there was a full moon last night. It's still pretty full tonight when you go out. You can go back and think about, well, if that's how bright those gravitational waves were from a pair of neutron stars that were 1.2 billion light years away. It's amazing. Now, over the past 2 years, they found a bunch of these. There are actually 4 pairs that are well identified, and there's a 5th one that is just right at the level of detection, so they're not 100% sure they really detected it. But 4 or 5. And that I'll show you now is the black holes that we knew about from studies of our galaxy and nearby galaxies and their masses. Nearly all of these are more massive than the ones we knew about. Now, the more massive something is, the bigger a strain it produces when it moves, right? The bigger, more it radiates. And so if it's twice as big, it produces twice as much strain. Strain is linear with distance, so you can see it twice as far away. It's not like now with energy, if I asked how much was in the waves, it goes down as the square of the distance. But the strain, that goes down as distance. So we gain here tremendously compared to measuring the energy. So that if something is twice as energetic, if it's twice as massive, we can see it twice as far away. That means we can search a volume that's 2 cubed or 8 times larger, right? So that with a more massive object, you have a much larger search volume. And that's probably part of this. But we don't know if there's a lot of debate about whether it's all of it and whether we need something else besides just stellar evolution and a big search volume. And there's Ray Weiss again. This was Nobel Prize number 2 for general relativity. There was Einstein did not get a prize for not even special relativity. Yeah, they didn't like relativity. It was too Jewish for them, they said. It was called Jewish science by a lot of the Germans at the time. And so, but it's everyone's science now, so now it's finally gotten its 2nd Nobel Prize for the actual detection of gravitational waves. Now, Europe wanted to join in the fun, and so they built their own detector, and they got it turned on in this last year. And there was the most recent of the black hole mergers that I mentioned there was this one. It's not quite as sensitive yet as the 2 ones in the U.S., and this one isn't as sensitive as Livingston. This one, they tried to upgrade them 2 years ago. It didn't go so well, so they brought it back, and Hanford never quite recovered from its upgrade. But so they're trying to upgrade again. You know, what they need to do to get these things to work is just unbelievably. If you saw just a tiny fraction of what they need to do, right? They need to completely isolate them from all the seismic noise, everything. It's incredibly difficult. So I'm just hoping that they'll come back in better, much better. They really get that factor of 2 that they're planning for the next year. We'll see. But nonetheless, to have that 3rd point is very crucial. Because if you want to know where they are on the sky, it helps tremendously. See, these big error circles, it's not really a circle, we usually use the term error circle. This is an error ellipse or an error blob, right? And there's a blob on each side of each hemisphere because you couldn't even tell which way it was coming from. There were two different directions. With just two detectors, there were two different directions that it could have been coming from. With a third detector, that's no longer possible. So these two objects have the European Virgo in place, and so you get a much smaller error region, and you can tell which hemisphere it's in, which helps a lot. But the fact that it's much smaller is crucial because you would like to go and search them with optical instruments. And as you heard Frank pointed out to you, Hubble has a very small field of view. Now, there are optical telescopes with larger fields of view than Hubble, but they're still not, large. They're not anything compared to the size of the sky. So you really need a good position, and this has helped tremendously. Now, we always thought that we knew about the Hulse-Taylor pulsar, so we always thought what we're going to see is neutron stars merging, and for a while we just got black holes. But late last year, 3 days after that last black hole that the Europeans saw, a pair of neutron stars merging was detected. That's what you're seeing here. They had masses about 1.5 and 1.25 solar masses. Neutron stars are typically about the mass of the sun, from a little bit less to about 2 times this mass of the sun. The objects are extremely compact and leave a single massive remnant. And again, they only lose 2.5% of solar mass to gravity. So they lose very little compared to what you saw for the black holes, because the neutron stars are not radiating nearly as powerfully because they're not moving as fast when they come together, and they're not as massive. Now, NASA's Fermi satellite, which is a gamma ray satellite, and Europe's Integral satellite detected a gamma ray burst 1.7 seconds after the merger. Now, you would think the gravitational waves should arrive at the same time as light. That's the prediction. Now, this is still amazingly good, because that came from 120 million light years away. So that's 1 part in 10 to the 15 that was off. So it's still very, very good. And we think, in fact, that it probably takes some time to create the gamma ray burst. You probably have to spin up a magnetic field. You have to break out of the neutron star. So it could well be that all of that 1.7 seconds is creating the gamma ray burst, right? And so they do exactly travel at the same speed. But that would be the prediction of the theory of relativity, that they should travel exactly at the same speed. And still, 1 part in 10 to the 15 is pretty good. But we finally got a neutron star merger. Now this is and Virgo, you see, it didn't see it at all. Well, this was important because it's the dog that didn't bark. Because they knew from the previous detection how sensitive Virgo was. And so they knew that in most of the sky, Virgo should have seen it. And so there was only part of the sky where Virgo wouldn't see it. And they could restrict it to that part of the sky. So in fact, the non-detection by Virgo was very helpful. We'll get to that in a minute. Now, what happens when 2 neutron stars merge? This is, here actually you're seeing the matter of the 2 neutron stars. And some of the matter is being just thrown off into space. Okay? Probably a few percent of the material of the stars gets thrown off during this merger. Now, this is very important because this material is, again, I told you earlier, we think that this material is highly radioactive. It comes off as just pure neutrons, right? And so it starts as very heavy elements. I'll show you that in a minute. And so it basically comes out and populates the universe with heavy elements. Now, it also radiates in the optical and the infrared, we think. I'll get to that in a minute. Now, did that right? Oh, I thought I took that out. But OK, doesn't matter. It'll show you this in a minute. So there we have the matter merging. Now here is a view, electromagnetic view of this is showing sort of the hot spots on the neutron stars. This is sort of an X-ray view of it. Now, this is produced by NASA, and it was for the SWIFT satellite, which is a gamma ray satellite, and they wanted to show, you saw that beam coming out of it. There has long been a theory that something we call gamma ray bursts, especially the short gamma ray bursts, may come from the merger of 2 neutron stars. We've never been able, there's no absolute proof of that yet, but everything we've seen is consistent with that hypothesis. We know that another type of gamma ray burst called the long gamma ray burst, they last much longer. We know that those come from the deaths of very massive stars. But this other type, this sort of much short gamma ray burst that lasts much less, lasts about a second, where the other one lasts typically tens, hundreds, or thousands of seconds. These short ones, we thought, come from the mergers of neutron stars, or perhaps neutron stars and black holes. We've never been able to prove it, but where they are, where we find them, all seems to indicate that they probably come from neutron star mergers. And Mario Livio, who many of you have seen, used to say, if the merger of neutron stars doesn't produce a gamma ray burst, what does it do? So that was one of the stronger arguments. But but now we may have evidence that it says, because it was that gamma ray, but the gamma ray burst was very faint. So it wasn't that beam was not, if it did produce a true gamma ray burst, that beam was not pointing at us. We were seeing it from a side. Okay, now here we see it sort of, this was produced by Hubble, by our own outreach office. And because we observed this, I'll show you later in a minute, we observed this with Hubble. So here's the neutron stars merging. Then they come together, they throw out matter. Now this matter is hot, and if you look at how much energy it radiates, it's about 1,000 times as much as a nova, which is a type of a dwarf white star that burps, has a small nuclear explosion occasionally, and that's called a nova. And then a supernova is a really big nova, right? But it's actually an explosion of a real true explosion of a star. And these novas tend to be sort of surface burps, surface thermal nuclear reactions. And this is about 1,000 times brighter, so it's been dubbed, the term most people use is a kilonova. Now, on top of that, you'll get the gamma ray burst, we think. We may or may not. I'll go into that in a bit. And then around that, you'll get, we think, a jet, quite possibly, a wind, a very strong wind coming out near the axis, very hot blue wind. And around it, you'll have this red material. I'll explain why it's the red, the neutron star material, why that's red in a minute. Let's see. Oh, right. But before that, let's see. NASA just couldn't resist. So I had to show you the feature-length film then. Well, it's not good feature-length, but feature-length productions, feature production scale. Oh, you have to hear this. Let's go back a bit. I'm going to go. Let's go. I'm going to do this again with a little less sound. So here we have the gamma ray burst. Here we have the two neutron stars merging, putting out gravitational waves. Now they produce a gamma ray burst, is the idea. Now you have this hot wind coming out and the kilonova in the center coming out. Now here you see these jets later on expanding very large. This may be crucial to what you will see in a bit. So first we had to go find the thing, right? And I was involved in the Hubble Space Telescope follow-ups, but a few of the people here were actually involved in searching that very day, right? And what a number of groups did was they said, okay, well, this is the region that the gamma ray burst could have been in. Here's the region that LIGO could have seen it in, and then there's the region that Virgo and LIGO could have seen it in. So that's how Virgo helped, right? And then you look on the sky in that region, and what the smart groups did is they said there probably went off in a galaxy. You know about how far away it is, because again they could tell us right away that it's about 120 million light years. They got it right on the nose, and so you could look for galaxies in that region that were about that distance away. And you could start with the big ones and work down to the small ones. And it was in a big one. And that's it right there, that dot, that extra dot right there. Now, lots and lots of telescopes. This was one of the biggest observing campaigns in the history of astronomy. Oops, I went too far, yeah. This was, we had 2 dozen observatories on the ground, the 3 gravitational wave observatories, and 7 space telescopes observed this thing, right? Because it was a big event. There were about 1,000 astronomers involved in all of the observations. But fraction of the total astronomical community was involved in some way or another. Most of them were just like, I work at the observatory, put my name on the page, right? Put my name on. But and the LIGO group itself is around 1,000 people. It's huge. It takes it's like a high energy physics experiment. It's incredibly involved, incredibly difficult to build. In fact, I should have gone. We'll get there in a minute. But I did show them, and I didn't go over what each of the contributions of the 3 discoverers were. The 3 Nobelists were in this case. So there was. Let me do Shift, Command Plus, I think does it, right? Yes. Go back for a second. There we go. So I mentioned it was like a high-energy physics experiment. Barry Barish comes out of the high-energy physics community, and his contribution was basically to make the thing work. He came and became the director and really brought it together. And Ray Weiss, as you heard, conceptualized the thing way back at the very beginning. And Kip Thorne is a theorist who really was behind much of the theoretical understanding of what you would see and how you would predict what you would see. And so that, as a result, and there was also Ronald Drever, who unfortunately passed away, but before this happened. But the Nobel Prize can only give, the way they have the Nobel Prize still set up today, you can only go to 3 people. So, and yeah, I don't know what would have happened if he was still alive. But no one, yeah, that's a problem. They talk about that, changing that, but they never have. Okay, so then it was observed by, and in fact, 6 independent teams discovered the object almost simultaneously. I showed you the first one, but within an hour or so, lots of other teams found it too. And it was observed from the gamma ray to the radio. Again, one of the largest observing campaigns in history. And this just shows you all the different wave bands it was observed in and all the different discovery images. Right? It's amazing. Okay. Oh, I've got to do escape, maybe. There we go. There we go. All right. So this is the Hubble image of that galaxy. And there is the source right there on this. Now, the host is a massive elliptical. It's named, or it's got a catalog. It's in a catalog. It was known before, was studied before. In fact, there was a Hubble image of it taken before this object went off. This explosion happened. Actually, only several months before this explosion happened, by chance. But and it's about 120 million light years away, as I said. The explosion is actually relatively far out on the galaxy, and elliptical galaxies tend to have lots of groups of stars we call globular clusters, very dense concentrations of stars. And we think that those are actually very good places to form binaries and massive binaries, and probably neutron star binaries. And we see lots of pulsar binaries and pulsars in our globular clusters in our galaxy. But as best as we can tell, this is not on top of one of those globular clusters. It just seems to be out in the field of the galaxy as best as we can tell right now. We're not down to we haven't gone down as deep as you could possibly go to see the very faintest globular clusters, because there's still light from the source there. Eventually, we'll be able to get a very deep image and tell. But you can go most of the way down to how faint a globular cluster would be, and there's nothing there. Now, this started out, as I mentioned, it predicted it would be blue, and in fact, that's what it was. And then it very slowly turned reddish. And lower, and the object became fainter but not redder after a few days. And what's really remarkable is that most of this behavior was predicted before the event. Dan Kazin, a while back, predicted that these objects will be very red, for reasons that I'll get into in a minute. And Mark Metzger has predicted that blue center core. It's really quite remarkable how well we had the theory down before it actually happened. Now there were competing theories, right? So you could say, okay, well, you could have sort of picked your theory, but these were the most likely candidates, and they turned out to be correct. Now, you'll remember that I mentioned to you that when you when you took this white dwarf and you put more mass onto it, you forced by the pressure, forced the electrons into the nuclei and turned the protons into neutrons, right? As the electron canceled the charge of the proton and they formed a neutron. Well, if this material is thrown off, it says, I'm free, the pressure's off. And the electrons pop out. And so it undergoes a radioactive decay. And here's a little, okay. And so over here is a little plot showing you the creation of elements as the material comes off the neutron star. And it just starts off very, very radioactive and very neutron rich and slowly moves over. Well, not so slowly, this is only a few seconds in real time. Turns into something very close to the periodic table. Now, there'll be lots of radioactive elements that decayed before we see them now on Earth. But if you look at the elements, the periodic table, you can ask, where did the elements come from? And we think that the blue shaded ones here come from exploding stars, by and large. These red here is largely left over from the Big Bang. There's a bit of cosmic ray fission. And then in the bit of the dark brown is sort of planetary nebula, dying low mass stars. But all of this yellow, we think now, is probably merging neutron stars. All of these elements here. And when you look at a normal supernova, its spectrum, say, is dominated by the iron elements. So you produce nickel and that radioactive decays into cobalt, and that decays into the iron that lasts. Now, and that produces a lot of the energy in a supernova, that decay. Now, these elements here are transparent in the optical, but they block the ultraviolet. So when you look at a regular supernova, it's bright in the optical, but it falls off very quickly in the ultraviolet. You see very little light of it from the ultraviolet because these elements absorb in the ultraviolet, but they let light through in the optical. Now these elements down here, the lanthanides and the actinides, they absorb in the optical, but they let light through in the infrared. And this was what Dan Kazan's group realized. So he said, if you're going to produce all of these things, you won't see it in the optical very well. You won't see those elements in the optical very well because they're going to block all the light. You'll see them in the infrared. And that is what we see. This is an HST spectrum of the kilonova. And that bump there was predicted. That's the lanthanides. If you have a lot of that lanthanide group, you'll get something like that. Now, in fact, the actual opacities and the states of the lanthanides are not well known. So it's going to take a lot more work in the lab to really sort that out, but it's approximately known. And something very close to this was predicted, right? Exactly how much, and it was a little bit different because it depends on how much do you produce, exactly how does it come out, what is the geometry, but it was very, very close to what we saw. So this is really an incredible agreement. This peak was very clearly predicted, and that was the major thing in the spectrum, and it was there. So we really think we understand the basic mechanics of what's going on, and we think that this is probably where most of the heavy elements of the universe come from. Now, of course, it depends on, we've seen one of these things, so we're sort of guesstimating the rate, but it's sort of comparable to the rate that we expected from neutrons, from pulsars, if you made a couple of assumptions about how pulsars come together. So it all sorts of agree. And so we think that we've got that. There are some mysteries still remaining, though, about this object. This is the light curve of the object in the optical and the infrared. The infrared is the red and green here, and the blue and the orange are sort of optical, not the best color choice. And they went down, over about 10 days, they just dropped off a cliff, right? Went down very quickly. But then we looked at it again about 100 days, and it was still there with Hubble. Now, why did we look at it again in 100 days? It was because other people had been looking at it in the in the X-ray and the gamma ray. The X-ray and the radio. This is the radio, and this is the X-ray. And they did not turn on until 10 days. And then they got brighter for a while. Now, it looks like they may have plateaued. Maybe not. So what we think, there are two possibilities, we think. One is that we're seeing that jet wasn't pointing to us, but now it's sort of opening up, or we're seeing it open up as we get with time, basically, which is a prediction that gamma ray bursts will do. As they slow down, they beam to a larger area. And if this jet is not just a perfect wall, but is shaped, like brighter here, and then it dies off to the edge, it would do this sort of thing. Another possibility is that the gamma ray burst never got out and produced a very hot bubble. And as that bubble starts out small, it's not so bright, but as it expands, this hot bubble has more surface area, and so it's brighter. This is basically what happens in the early stages of a supernova, too. They get brighter as they expand. Now, so that may be what's going on here. I think because of if short gamma ray bursts, we think that they're probably related to short gamma ray bursts, and therefore, by the numbers we've seen, there can't be too many that you would miss as gamma ray bursts, because otherwise the rates wouldn't work out between the mergers and the short gamma ray burst. But it's possible that, in fact, this doesn't have a gamma ray burst at all, but that the gamma ray burst got smothered, right, never quite got out and produced a big expanding cocoon of hot material. But there's a good chance we'll be able to tell by the shape of the light curve later on. It may fall off faster. We probably will fall off faster if it's a gamma ray burst. All this depends on the shape of the jet. Now this gets into the complicated stuff. Astrophysics was sort of, there's a famous astrophysicist, Sri Kulkarni, who believes that the best astrophysics is slash and burn, because you can't do real experiments. So you go and it's easy to get the basic idea. It's very hard to get the details. So we've got to sort out the detail here, right? We know it's merging neutron stars. We know we got lots of material thrown out. We've got electromagnetic processes going on. Exactly how it's working is going to take a lot of work, because we can't just go and take two neutron stars and merge them in the lab and see what happens. Yeah, it's just not part of the budget. But again, we may know by the end of the year because of what's going on. And again, we'll probably have, because the way it falls. And again, in a couple of years, we may have many more. Okay, so here are the blue here again are the black holes that have been seen by LIGO. Here are the black holes we saw before LIGO. Notice the pattern? Yeah. And then here are the neutron stars that we've seen before. These two neutron stars are right in the same mass range as all the other neutron stars. This is probably, they don't show errors. This has an error bar that could get it down to about 2 solar masses. We think about somewhere around twice as massive as the sun, maybe a little more than that, is where neutron stars collapse down to black holes. We don't know for sure. Maybe we'll learn as a result of this sort of work. These two objects did merge to something of more like 3 solar masses, so we think they probably merged into a black hole. How quickly that black hole formed, though, is an important question which we don't have answered fully yet. And the gravitational waves detector we have isn't sensitive on the high frequencies we need to really get to that. Did I not? Yeah. So, wait, let me go back. If I can get it to, it should have played. Where did I put it? Yeah. Should have been. Let me see if we get it to go. There it is. But I'm hoping to be played. Oh, you're not seeing it now because I switched the mode. No, oh, that's a shame. It takes about 30 seconds though. It's the sound of the neutron stars merging. And it worked on, it may have gotten lost in the transfer to this machine from the desktop. It goes, it's actually a pretty good imitation. Oh, there you go. And that's about the 30 seconds, so it didn't go off earlier for some reason, or we missed it. My talking and it wasn't very loud. We can do it again. We just have to wait a minute. Because you see this, okay, let me go back and, the recording that they got is about 30 seconds long. And so it takes half a minute for it to really show up. these neutron stars, you know, they just don't go off when you want. There you go. And it was just very soft and much lower before that, but it was just hard to hear with this setup. It starts out very low but it starts out sort of off. The reason this is longer is really because it's better suited to the frequency band that the LIGO detector can detect. There's too much bass really in the black holes for LIGO, and unfortunately, if this had more treble, it could get the actual spin down and merger of the two neutron stars, and you could really see, did it form a black hole, and what is sort of the equation of state of the neutron stars? That is, how big are they? That was something we'd really like to know. I don't think LIGO, that may take the next generation to do. Okay, let's, probably faster to do this. Plus, yeah. There we go, we just saw that. All right, yeah, that's where we were. Okay, so now there's another thing that these neutron stars might do, and that's help us with cosmology. One of the really important questions in cosmology, which turned out, we knew it for quite a while. You might have heard about this big argument between Sandage and what is the Hubble constant, which is how fast is the universe expanding locally? We know it's expanding, and we know the acceleration of the universe is actually expanding with time. But the actual velocity locally, how fast is it expanding locally, is an important issue. And it turns out that if you look at people looking at the cosmic microwave background using satellites to measure the cosmic microwave background, so the Planck telescope, the European Planck telescope did a very accurate measure to the cosmic microwave background. And they have to solve many things simultaneously, but when they do that, they get a number of about 67. Now, when kilometers per second per megaparsec, and a megaparsec is like 3 light years. So if you're 3 light years away, you're receding from me at about 70 kilometers per second. Double that, so 6 light years, you tend to go away at 140 kilometers per second, and on and on and on. Now, the number that Adam Rees here, maybe you've heard speak before, he's been measuring, and he won the Nobel Prize for the expansion of the universe. I was on the other team, Saul Perlmutter's team, but Adam's still a nice guy. But the number that you get, that Adam has gotten, is more like 73. Now that's just it, that's 3.8 sigma, say the term that 3 sigma is sort of like where you start getting, this looks bad, right? Now 3 sigma should be, if your world was just statistics, Gaussian statistics, 3 sigma would be, that's definite. The world is not. Things go wrong. So really 5 sigma is like beyond any doubt in real life. But 3.8 sigma is getting pretty serious. So, and it turns out that it looks like multiple experiments it looks like the cosmic microwave big measure, when you're measuring the universe very far away, you get a slightly different answer than when you're measuring it closer in. So it may mean there's something wrong with the model that we're using. It could be something as simple as that there was a particle that used to exist, that decayed at maybe 100,000 years in the age of the universe, and it's no longer around, a massive particle. We don't really know. It could be something more interesting. It could be just that you really need 5 sigma. But the interesting thing is that, as I mentioned to you, you can tell, by measuring the gravity wave here and how strong it is, you can get an estimate of how far away the object was. And this is from that single object, this bar here, and this is that line is the Planck measurement, and this yellow bar here is Adam's measurement. And you can see that this is only one object. Adam has dozens in here, and so if you could get many more, and if you could get the systematic errors down on these, there are some errors to worry about, and so it's just starting now. But you might have a completely independent measure. And with the local observations that the type Adam does, you have to sort of use a distance ladder, use a couple of different objects to really build out how far your things are. This is a direct physical measurement of the distance. So it's potentially very powerful, but it's tricky to do. So we'll see. But it's possible this will give us another way to really get at this physics, this cosmology. And the term that's been used, I wrote too far. That's just sort of cute. They're called, because of that, okay, so coordination is like not my greatest ability. All right, so these standard sirens, this chirp, it's also called a chirp, this right? So those are standard sirens is the term that's being used because you can tell how far, right? You can standardize them, how far away they are. And that would be the idea. So LIGO and Virgo are being upgraded. I mean, LIGO will return in 2019. It's expected to be 2 or 3 times more sensitive. Now, as I mentioned to you already, the strain, if things are twice as far away, they're half as powerful. So that if you have something that's 2 or 3 times more, can measure strain that's 2 or 3 times smaller, you can search a volume that's 2 cubed or 3 cubed larger, right? Radius turns into, you cube the radius to get the volume. And so you get, the volume goes up by a factor of 8 to maybe 30. So instead of 1 neutron star, merging neutron star per year and a few black holes merging per year, we could be seeing 1 neutron star merger per month and maybe 1 black hole merger per week, right? So it could be rather busy. Now, what's going to be coming in the far future, in the 2030s, say? This is a plan. This is called LISA. It's 3 satellites forming an interferometer in space with arms that are about 1 million miles long. And it's in a trailing orbit behind the Earth. And it'll be able to detect merging black holes in distant galaxies as well as white dwarf binaries merging in our galaxy. And now this may also look crazy, but there was a satellite, the Europeans with some American help sent up what's called a LISA Pathfinder, which tested the sensitivity of the detector, right, and how quiet they could make the whole system. And it far exceeded the goal of what they wanted for the Pathfinder. It in fact met and even exceeded what they needed for LISA itself in this first try. So this looks really doable. That's an incredible achievement that in this first try, right, they found that they were doing better than they wanted to do in the thing that they're going to do 10 years from now. So we may, somewhere in the late 2020s, 2030, we may actually have that thing flying in space. I don't know where it went, but it went flying into space. I don't know where. Okay, now, so there you have, there's LIGO, and then you have, this is, LISA is here, can get these things. Now, you can do other things to look for gravitational waves. Pulsars, again, clocks, and they're all over the sky. And so if a long wave comes and passes by, right, it'll affect all of the objects in one way, and the other way, right? So it's stretching, it's making the space. So, for example, the pulsars in this direction would look further away, and the pulsars in that direction would look closer to us. And then change right, it would change the other way. So you could potentially use this to look for very low frequency gravitational waves. So with sort of things with like over time spans of years that as they pass the Earth. And those would be found those could be produced both by binary black holes in galactic nuclei as they're merging, not quite at the end, but as they're close to merging. And then there's prediction that the early universe would have radiated, the actual Big Bang would have radiated gravitational waves. It's basically Hawking radiation from the horizon, event horizon of the universe. So if you want to blow your mind, you can just think about that. In fact, for a while, there was an observation called the BICEP. Some of you may have heard of this. There was a observation of the cosmic microwave background from Antarctica, and they thought they had found this. They thought they had found evidence in the cosmic microwave background of just that radiation. And that would have been like 4 Nobel Prizes wrapped in one. And it turned out in the end it was dust in our galaxy. dusts, it's just a pain. There are people who are astronomers who, they get all upset when I say that sort of thing, but because they're astronomers who like study dust. I just, just give me a clean galaxy. But, all right. All right, I love that effect. No matter what you say, it's got to, you're right. It's important. All right, so the detection of gravitational waves has given us new insights into stellar astrophysics and remarkable confirmation of general relativity, and may give us a new test of the cosmological model. Yeah, really. We have seen massive black holes in abundance that we did not expect, right? And that's going to tell us a lot, probably about probably about stellar evolution, maybe about primordial black holes. We have seen a neutron star merger produce a kilonova, confirm the suggestion that the majority of the elements in the universe are formed by neutron star mergers. We're not sure if we've seen a GRB associated with this neutron star merger, but we should know soon. And there are going to be, if LIGO, this upgrade succeeds, it doesn't go backwards but goes forward, we should have lots more to test, right? And some of those should be pointed at us. So that will help, the statistics alone will help us there. And so again, the prospects for the future of gravitational wave astronomy look very good indeed. So thank you very much.
Okay, so we have hit our sort of usual limit of 9:30. So if you need to leave, please get up and leave. We went on for a while. For those who want to stay and ask some questions, we have a few questions. I'm going to start with a question from online. So let's see. Where's Brenda's question? So Brenda asks, if there were two black holes in the center of our galaxy that merged and emitted gravitational waves, what, if any, effect would this have on Earth?
So I don't think it would hurt. I don't think you would notice. Because we're small, and so the stretch is very tiny. But boy, would the gravitational wave detectors have a field day.
Yeah, they would.
They would have a yeah. So I haven't done the calculation. I don't think seismologists would know it. Do you have a question?
No, she wants, just in case you guys need a refresher for this, Nancy brought up this book, and it's called General Relativity for Babies, in which one of the last parts of it is about gravitational waves, okay? And so I wanted to thank Nancy for sharing that with us so that we could all learn about
That is, they are so advanced these days.
Other questions that we have over here.
Yes, I have a question about, he referred to stretching, the rarefication and compression physically by virtue of these gravitational waves passing past you. So would that be indicative of a polarization of the wave? And secondly, if it is there are there other modes of polarization for gravitational waves? And if that's true, does that indicate that gravitational waves are actually a superposition of two or more waves?
Okay, I got to try and repeat that for the online audience. You talked about the compression and rarefaction of the wave. Does that indicate the wave is polarized? And if so, does that mean that the waves are superpositions of polarization states?
Yeah, so the average wave you see is a superposition of polarization states. This is one polarization. You stretch like this, and this then 90 degrees away. Now, hopefully, if this works, yeah, you can rotate by 45 degrees, and then the stretching 45 degrees and the expansion 45 degrees, that's the other polarization. That's the way gravitational waves work. They're not quite like the dipoles of electromagnetism that you think of, where it's typically like a vector, one direction, and then it's the 90 degrees. Here you've got basically, electromagnetism is called dipole radiation. It's basically along a line. This is a quadrupole. It's basically a sort of elliptical shape, right? A two-dimensional shape that radiates. And so you get the polarization is actually just the stretching and compression being rotated by 45 degrees. And the polarization is important in understanding the orientation of the object from you. Yeah, that right, and so when you measure these gravitational waves, trying to measure the polarization is important if you want to solve for all of these parameters of the orbit.
Is it possible to have one and two modes of polarization?
No, these are, in general relativity, these are the two modes.
Okay, down here.
I never ask a question. Usually in a massive nova, supernova, we have neutrinos predicating the visual. Do we have anything preceding the
Okay. No.
So, all right, let me repeat it. So in a supernova, the neutrinos are part of the thing that blows the star apart. Is there a similar release here?
It probably was, but our neutrino detectors aren't sensitive enough to detect it. So the neutrino detectors can detect things in our galaxy and in the nearby galaxies. The things we're seeing here are too distant, we think, for the neutrino detectors. But it's an important question you ask in the way that, so gravity, this is called in the astronomy community, this is called multi-messenger astrophysics, in the sense that you're using different types of particles or form, right? So electromagnetic radiation is one messenger, gravity is another messenger, and neutrinos are another completely different type of messenger. And so if you had something close enough, or we had much more sensitive neutrino detectors, you could get that.
Yeah, I mean, we talk about gravitational wave astronomy. Neutrino astronomy is also a very infancy type development.
That's right.
And, you know, there are talks of being able to see neutrinos from in the early cosmology, right?
Well,
And such. So, I mean, there's possibilities of other non-optical.
yeah,
non-
especially from,
non-magnetic
say, a supernova going off in the local group. In fact, right, so neutrinos were detected from supernova 1987A.
Right.
Right, and so a handful, but they were detected. But that was a very close galaxy, right? And so that's the problem.
Question over here.
In the E&M world, there's a B field created from a relativistic effect of an E field. But since in the gravitational world here, that is the relativistic, it is relativity. Is there no analog to a B field?
Not really, no, and it's not quite analogous. And in some ways, I was thinking about this earlier. I think that part of it is also that, in fact, what we've learned from quantum mechanics is that the way to think of it isn't really as an it's to think the electron E and M modes, the E and B modes are actually different derivatives of a thing we call, of a potential, what we call vector potential. And it's only quantum mechanical. People thought that was just for a long time, people thought that was just a mathematical creation. But there are some quantum mechanical tests where there's no electric field or magnetic field, but there's just this potential, and it affects the way quantum mechanical particles propagate. So that, in some sense, may be the real deal, and right, rather than the E and the B. And so in some ways, it's more analogous that way. But yeah.
Okay.
But there's no real there is no real different. It's just a different polarization. Yeah.
All right, two more questions here and then over there. Yeah.
You talk about how you deduce the various parameters from the study of the gravitational waves, but is that true of directionality? That seems like it's not as clear, as clear a reasoned path to directionality of the object out of the gravitational waves. Is that correct?
So you have to use timing, basically. That's right. So the major thing is that you say, okay, the wave came, hit me here, and then it hit me here, and then I know, so that if it hit here first, then it had to be sort of, you just draw circles, right? Of where is it going to be that much closer, right? And that third object gives you, that's why the position, it's like if you do reckoning, right? If I tell you the distance of something is from two objects, you'll get 2 points, right? Two solutions. You draw two circles, and the intersection of two circles is usually 2 points, right? But if I give you a third point and tell you that, you get one distance, and the same thing happens here.
Right, and wasn't it sort of like a confirmation that gravitational waves travel at the speed of light by the timing between Hanford and Livingston?
No, well, yeah, I guess the better one was the 1.7 seconds of the gamma rays, and the gamma rays coming only 1.7 seconds after the arrival of the gravitational waves. That's much more precise and proportionally.
Right, proportionally over there. All right, and Peter, you get the last question.
Yeah, okay. Any chance gravitational waves could be a useful source of energy?
All right, any chance that gravitational waves could be a useful source of energy?
So as you saw this, I mean, well, so, this is not really. I mean, because just like the moonlight wouldn't be a useful source of, right, the full moon isn't a useful source of energy, so that's what we're sort of talking about. But even so, harvesting that energy is not easy. Right? I was saying, well, if you could, focus it the way you could focus electromagnetism, it would look like a point source as bright as the full moon. But focusing in gravitational waves is not easy. So, yeah, yeah.
All right. So there's a lot of energy at the source, but we'd rather keep it over at the source than get too close.
So the space-time, it turns out that space, if you do the calculation of like space-time, there's a lot of energy, but space-time doesn't move very much. And you can say, well, how stiff is space-time? And it's about 10 to the 20 times stiffer than steel.
Oh, okay.
Yeah, it's like, but it's like a billion million or something. A billion million 1,000, yeah.
All right. So space-time is very hard, very stiff.
Yeah.
Only translates a bit of the energy.
10 to the 21, so yeah.
All right. So next month we have star formation in Orion, June, I think it's 3rd or something like that. It's on the calendar. Hope to see you all there. You have now just been indoctrinated into the brand new, brave new world of gravitational wave astronomy. Let's give Dr. Fruchter one more hand.